Good afternoon. I hope I think there's lots of light up here, so I hope you can see me. Now I can't see everyone very clearly in the audience because I don't think this lighting is up to scratch. There are no windows. But it's okay, so it could be worse, I guess. So what I'm going to do today, I think I'll go over go through people's names, go through the list of names again. But was that a little brighter? Gee whiz, yeah. Okay, someone found that's lighting up the aisles. I don't think that was. Anyway, the more light on the subject, the better. I don't know if you want to be referred to as the subject. Maybe that's better than the object. I don't know. Well, but the object of the course. What I was planning to do is start off with discussing a homework exercise, namely along in the theme of there only being one theorem in linear algebra over an arbitrary field. Forget about the canonical Jordan form or canonical rational form, because that's not linear algebra. That's ring theory. Okay, it's very nice, but it's so linear algebra is over a field, linear operators and vector spaces. But just well, it's true that look at polynomials with coefficients in a field, then that's a principal ideal domain, and you can, if you take a vector space with a linear transformation, then it does give you a module over the over that ring, and if it's a finitely generated vector space, then it'll be a finitely generated module, and it could even be could be an infinite dimensional vector space. There's the clue. This applies also to infinite dimensional vector spaces. If there is a single vector together with the or a finite number of vectors, which together with the operator generate all vectors. So that it's a sort of a rudimentary infinite dimensional theorem. Yes, question. What kind of problem?
Like our solutions to the problem.
Well, yeah. Well, by the way, the problem set was only a suggestion, so I couldn't really take up that those particular problems. You're supposed to. I mean, one problem you were supposed to consider is the one I'm just going to talk about now. That's but I don't think that was included in Mr. Lau's suggested list. So it was just saying that an example. It was giving another example of two linear algebra theorems which are trivially equivalent. Okay, I mean, one of them is well known. It's the fact that dimension exists, right? The dimension, the number of elements in a basis behaves like a dimension. Take a direct sum of two vector spaces, then the union of the two bases is in a natural sense is a basis, and so the dimension is additive. So that's one theorem about the vector spaces, and the and another one is what I was just which is directly related to the course, namely the K0 of a field is what? Yeah, it's a group, right? It's a Abelian group, and in this case, it's the group of integers, and this is supposed to allow you to prove that in a trivial way that dimension is number of elements in the basis is additive and direct sums. In other words, and in particular, is independent of the basis. And just to give you an, I was hoping, I'm still hoping. I haven't seen what people have been handing in. As of yesterday, someone had already given me a list of exercises, quite a few pages. But today I'm hoping I've been too busy with a workshop to look at my email yet. But anyway, um, I was hoping that someone might, for instance, take the theorem, the basic linear algebra non-trivial theorem, that in a finitely generated vector space, injective for a linear transformation implies surjective. That's one statement. And the other statement is you just interchange injective and surjective, and it's still true. Okay. And so how do you go back and forth between those two? How do you interchange injective and surjective? Well, for finitely generated vector spaces, there's a simple way to do that. How many people know how to do it? Yes. You're Abu? Well, I'll have to, I'm wanting to keep track of people's names. Are you Abu? Sabek. All right, well, at least I'm right that I should know your name. Okay. Right. That's called second order rightness. Okay? This is a second order theorem in linear algebra that all first order theorems, all non-trivial first order theorems are trivially equivalent. And so, Sabek, what were you going to suggest? Well, okay, but that's sort of changing ground. I mean, you're saying you want to prove that injective implies surjective, and so you're saying take some other non-trivial. Well, of course, you're allowed to take any other non-trivial theorem and use it to prove this. But I was suggesting a particular other non-trivial theorem, namely where you just interchange injective and surjective. Okay, so you have to look twice. Look twice to make sure there are different statements, right? So one is injective implies surjective, and the other is surjective implies injective. And now you could go by way of some third non-trivial theorem, but in fact you can go back and forth. There's a simple operation with finite dimensional, finitely generated vector spaces, which which allows you to interchange injective and surjective. So how many people think they might be able to suggest what I have in mind, to put their finger on what I have in mind? Yes, Daniel. Well, okay, that's I'm very happy to hear that answer, because that's the other sort of new fundamental, new non-trivial theorem. Okay, we're adding to the number of non-trivial theorems. I don't know if linear algebra students how will be thankful to us, but anyway. So you're suggesting a technique of index. All right, I would suggest that there's a more elementary way of doing it, and it is important that the vector space be finitely generated. Okay, but is everyone familiar with what the dual of a vector space is? You took linear functionals, and they're a vector space. Linear mappings from the vector space into the underlying field, the basic field. Okay, and well, in general, it's an infinite dimensional vector space, and the dimension of the dual space will not be the same. Okay, at least if it's a countably infinite dimensional vector space, then the dual vector space does not have countable dimension, doesn't have a countable basis. But if it's a finitely generated vector space, let's not talk about a base. Let's not talk about the dimension, because that's one existence of dimension with important properties. That's one of the non-trivial theorems. Okay, you don't want to start running the risk of cheating or having a circular argument. But okay, so now not only so if you have a vector space. If two vector spaces, V, let's say just V and V, because we're talking about transformation from the space into itself. If the dual space is V star, then, well, first of all, if it's W, V going to W, then you have, well, V star the opposite direction. Because if you have a linear functional there's a linear functional on if F is the field. If you have a linear functional on W, then you compose it with the map, you get a linear functional on V. So it goes from V star, goes from W star to V star, okay? So, and furthermore, if you take the, take the double star, then that's still, you have the same theorem, right? But it reverses again. And in fact, in finitely generated, in the finitely generated case, V is canonically isomorphic to V double star. It's always contained in the finite dimensional case it's on. And W is the same as W double star. But if you look at the T and then T star, the T double star is equal to T in the finite dimensional case, finitely generated case. But the point is that if you look at T and T star, T makes sense for T to be injective, right? Well, that's exactly the same as saying that T star is surjective. And the thing that, and furthermore, these are exercises. If T is surjective, that's the same as saying that T star is injective. So saying both, saying that the T is both injective and surjective. Well, we're not talking about both. We're not talking about both. But we're saying that injective implies surjective. Okay, injective implies surjective. But then going down to T star, that says that you can interchange the two words. So that says that surjective implies injective. But but that's we're talking about an arbitrary T. The T star is an arbitrary transformation. Okay, and this is not the same, not canonically the same as W. It is isomorphic. There is an isomorphism, non-unique. But the point is, it's an arbitrary finitely generated vector space. Okay, so we're saying that if it's true for even the dimension, the same. We don't have to worry about that. For arbitrarily finitely generated vector spaces, surjectivity implies injectivity. Then for arbitrary, it's the same. It's a corresponding family. So and the two words get flipped. Injective and surjective get flipped. So there's an example of an essentially trivial proof. It's just a bit of hand waving. It's a good exercise. Okay. I'd say even if I've gone over it, it's worth writing out. And you could even do it by this afternoon if you haven't got hand in exercises. I don't want to insist, by the way, too much on deadlines, but forget I said that. Okay? All right. So that's an example of what this multifaceted exercise is, the fundamental theorem of linear algebra, in quotation marks, because I think someone even in 1 year managed to locate such a name on the internet, and something was called that, so maybe rank nullity or something. But so it's a slightly unfortunate choice of phrase. It's supposed to be something bombastic, which summarizes all of linear algebra in a single statement, and the fact is. And the trouble is that all the non-trivial facts, they look very different, especially when you start talking about index. But then what you were thinking of is that the vector space is finitely generated if and only if every linear operator has an index. And then in that case, it means the kernel and the co-kernel are finitely generated. And then in that case, in the finitely generated case, the index is always what? Yes. Okay. Now that's equivalent to the rank nullity theorem, if you like, or it's equivalent to any one of these other non-trivial theorems for arbitrary fields. And so the one I'm suggesting is that A0 of a field, when you're putting up for consideration, this K0 of a field is isomorphic to the group of integers. Okay, just a group without any order structure. And and so there are two parts to the exercise to prove this is true. Well, we've discussed why it's true, right? To compute the semigroup in terms of finite, in terms of direct sums of finitely generated vector spaces, which is the same as finitely generated projective modules over the field. So you look at finite. So we just take as a given that, you look at the semigroup isomorphism classes of finitely generated vector spaces with direct sum. And you notice that up to isomorphism, it doesn't matter how in which order you take the direct sum. Or if you take three, it doesn't matter how you bracket two of them. Okay? So, so that's a semigroup, a abelian semigroup. And you take what's called the universal enveloping group. Some people associate the name Grothendieck to that construction, but it was discovered for absolutely general groups 20 years before Grothendieck used it. It was Grothendieck's claim to fame, or his justifiable claim to fame, is that he used the enveloping group to give you the K group, and in the setting of algebraic geometry, it was revolutionary what he could do with it. So if people talk about the Grothendieck group as just as a way of going from a semigroup to a group, then he'll be rolling in his grave. No doubt about that. But okay, but and in the case of the if we're doing this calculation, then you get that the semigroup is Z plus, including 0, and the enveloping group of that, we've known from early in our education, that the enveloping group is the integers, right? Okay. And so the question now is to go backwards. Does this imply that that the Murray von Neumann semigroup say defined in terms of module version, means finitely generated vector spaces? But because this is the simplest way of defining it. So you take finitely generated vector spaces and take direct sum. This is isomorphic to Z plus. Okay. Sometimes people write Z greater than or equal to 0, mean including 0. But if you're taking the enveloping group, it doesn't matter too much whether you include the 0 in the semigroup. It doesn't matter at all. Semigroup doesn't have to have a 0, whereas a group has to have a 0. So if you take away the 0 from the semigroup, then the group just puts the enveloping group just puts it back in. Okay, so this is a one part of the sort of very ambitious bird's eye view of linear algebra that I've been trying to promote. Okay, so that's what I wanted to. That's how I wanted to start off. But let me go through names and please excuse any awkwardness with the pronunciation, locating people. So Abigail Arsenault, thank you. Alexander Bullen, thank you. Jing Quan Kao, thank you. Jack Tironi, is that good pronunciation? Should it be Cironi or Tironi in English? Cironi? Yeah, okay. So the trouble is sometimes I can coach too much on other languages, and I do it like no one should ever say Einstein, right? They might think that you're inviting them to go for a beer, something, I don't know. But, okay, but on the other hand, if it were 100% English sort of transliterated, it would be to Einstein. So it's a difficult world to negotiate. The world of science or science students, I guess, too. Yeah. All right. Yuja Ching. Oh, yeah, thank you. Carissa Cho Lee. Oh, thank you. Siddharth Dagar. Okay. Daniel Dima. Emil Shredfeld. Sorry, it takes me a while to scan. It's really intimidating when Google says how much it took to display a whole screen full of sources. Some number of microseconds. Well, now maybe with me it should be milliseconds, but I don't know. That's okay. Justin Foos. Thank you. Sabek Germain. Charles Griffin. Thank you. Yes. Tan May Goer. Thank you. Henry Hu. Zhao Huang. Thank you. Sorry, yeah. Yeah, okay. What do you usually use? Okay, I'm sorry, I still can't, it's a large room, I still can't catch everything. A little noise, that's just an excuse, I guess. But if you come up afterwards, and I mean, at some point, if you ask me a question, we'll figure it out. Jalal Kasab. Thank you. Alexander Cole. Zhao Shang Lin. Yifei Lu. Thank you. Luke McCutcheon. Thank you. Abu Bakr Mohidin. Thank you. Madariso Mulaisho. Ruben Navasargan. Sorry? Oh, yeah, thank you. Sorry. Jonathan. You know, I never got the right pronunciation of NG. So, Ing. Okay, good. And Rishi Prakash. Thank you. How are you on Shi? Thank you. You're HY. Okay, good. Hotel Su. I have a former student named Su. But also the and his name it comes up in C-star algebra theory a lot, so it'll come up in the course when I'm reporting on recent classification theory. So after this, I was planning to go into Grimm's theory of classification, okay, for matrix algebra, generalized matrix algebra, infinite tensor products of matrix algebra. But there's a whole story going from there very far into the future. Well, very far into the field of simple C-star algebra. And there's there's something called Jiang-Su C-star algebra. And if the tensor product of a given one with that it doesn't change it, then the K0 and K1 and traces classify it, okay? They tell you what it is. If it has to be what's called an amenable algebra, and simple, but otherwise, okay. So this is something it's not in the book because the book is too old, okay? Well, the book has AF algebras, which was the very next step after Grimm UHF. All right, so see if I can find where I was. All right. Well, okay, that's easy. By the way, Jiang is Jiang. Su is SU. I've been in China a number of times, and there's Shanghai, it's a whole province. And then north of it, there's what do you suppose the next province is? Jiangsu. Okay, the Shanghai, we have had a meeting. There's been a lot of meetings in Shanghai, very important center for C-star algebra. So it's well located. Huh. Okay. And by the way, in physics, having two algebras close together, that's how you just join the physical system. So somehow Shanghai and Jiangsu, it's almost as if they form a joint system, which is okay. But sometimes my imagination gets the better of me, I'm afraid. Okay, so she drove soon. Thank you. Lawrence Tsai. Thank you. Larry, yeah, fine. Amy Wang. Thank you. Hongbo Wang. Thank you. Xiaodong Wei. Jikam Wang. Thank you. Jiqi Zhang. Okay, thank you. All right, so we've already talked about matrix algebras, algebras of square matrices form an algebra over the field that forms the entries. So the entries with complex matrices with complex entries, then they form a complex algebra. In fact, it's a C-star algebra with a natural norm and star operations. But the classification theory for the BIM algebras and even the general AF algebras, we don't need to do it at a C-star algebra level. We can just talk about pure algebra. Okay, so looking at the finite dimensional matrix algebras as algebras, just algebras, and finite direct sums. And then you have two such algebras, finite direct sums of matrix algebras. So this is what Bradley did. So he looked at finite direct sum of matrix algebras. Then he mapped it in some way into another finite direct sum matrix algebras. Maybe with doesn't matter so much, but maybe with an injective map, so it's larger algebra. And then another larger algebra again, which is a finite direct sum matrix algebras of various sizes. Probably most likely the size is getting larger. If there's only one matrix algebra at each place, then the size has to get larger, or the algebra has to stay the same at every stage. I mean, that's just saying if you have a sequence of numbers, natural numbers, it either has to get strictly larger all the time, or it's the same arbitrarily large. If it's real numbers increasing, it doesn't have to get arbitrarily large without continuing without. Whereas if it's natural numbers, then if it doesn't get arbitrarily large, an increasing sequence, then after a certain point, it's always the same. Okay, but so that's how. Well, but if it's finite direct sums, they don't always have to get large. If the inductive limit is simple, in the case it's simple, meaning no non-trivial two-sided ideals, then the individual matrix algebras have to get large, at least if it's unital map. So this is taking the unit into the unit and so on. Let's assume that. Okay. Well, then if you have an increasing sequence of algebras, just like an increasing sequence of sets, it makes sense to take the limit, pass to the limit. Okay, the infinite union of increasing sets. Now, strictly speaking, you have to give a definition of it. If it's an increasing sequence of subsets of a given set, of a fixed, of a set, you know what it is, then you can just take the, you don't need to define, don't need to construct the union of the increasing sequence, it's just there, okay? That's that's how set theory works. But now, if there were something called a largest set, there are largest sets that contain everything, then all your increasing sets along the way, they'd be contained in this big set, so you could take the union in the usual way. But you can't do that. We discussed earlier why there's no such thing as the largest set, right? Because if being a set means you have a cardinal number, and you can do cardinal arithmetic. And whenever you take an exponential of one cardinal not equal to 1 or 0 by another one, you get something which is strictly larger. Okay, so there's no largest cardinal. So, but let's not worry about how you construct the abstract union of a increasing sequence of sets. By the way, it's the same problem for the disjoint union, and maybe people are even more familiar with the disjoint union. And in fact, if you, I guess you could probably use the disjoint union to construct the union. But let's not worry about that. So that's what these algebras are. They're the AF approximately finite dimensional algebras, the non-C-star version. Just take the union. Because once you have the union, the finite stages all have compatible algebra structures, so it's pretty light work to extend the common finite stage algebra structure to the union. Okay, because any elements, algebraic operations involve finitely many elements, and the finitely many elements will always belong to a certain finite stage. You just already know how to operate on them, combine them, and it doesn't matter which finite stage you take because the finite stages are compatible. All right. So, so what did Glim do? Am I on the camera? Okay. No, right, yeah, okay. I go this way. See, things are improving. The first day I had the feedback, but that seems to have got fixed. All right, so I was going to say, what did Glim do? Well, Glim did an enormous number of things. He did fundamental C-star algebra work in a number of directions. And then this was his PhD thesis, the UHF, uniformly hyperfinite. That's a way of expressing the union of finite dimensional algebras. So he did this, and then he, this was his thesis. Then he did something. He did a lot of fundamental work on what are called type 1 C-star algebras, which if you look at UHF algebras, if you include the finite matrix algebras, then those are type 1, turns out, and the otherwise they're not. Okay? Type Roman numeral 1. a fundamental bifurcation in mathematics between so for C-star algebras, if it's commutative, then it's type 1. If it's simple and not finite dimensional, or not the compact operators, then it's not type 1. So he had a definitive paper on type 1 C-star algebras, finding a whole lot of equivalent positions. It's quite surprisingly different on the C-star algebra referred to be in the class of type 1 algebras. And then he, with Arthur Jaffe, he collaborated on a series of papers on quantum field theory using C-star algebras. Construct quantum fields. And how many people have studied physics? Okay, well, after all, indirectly, if we were studying mathematics, we're studying physics. Okay, but it's very and recently, in recent years, well, maybe for a long time, mathematics has boiled over into physics. I mentioned earlier, maybe the first day, one example, the knot polynomial of the late mathematics fields medalist Vaughan Jones. It was first there was a variant for ordinary knots. Okay, so you could distinguish the knot in your left shoe from the knot in your right shoe, assuming that you did the mirror image knots. And that was the first time those two knots had been distinguished. Okay, because Jones knot invariant. Well, there was no way of visualizing it. There was an inductive way of calculating it, so using projecting a knot onto a plane, keeping track of when two lines cross in the plane, which one is on top. Okay, so that was not the crossing. You keep track of the crossings, and you can compute the polynomial. Well, whereas something called the Alexander polynomial was very easy to understand geometrically, and it didn't distinguish these two left and right knots, left and right versions of the same knot. But by the way, I have a left-right comment in my email, right? That the left modulo construction of K0 gives you the same answer as the right modulo construction. And the way you prove that is to show they're both equivalent to doing it with idempotents. The idempotents are there's no left-right. Okay, so well, what Witten did, and he got a Fields Medal for that, well, partly for that, is, by the way, some of you probably know this story as well as I do. What he did was find a quantum field theory. We're talking on the subject of quantum field theory. He found a quantum field theory method of calculating the Jones polynomial. Okay, and it was quite simple. You have you don't have to project the knot onto a plane. It's just a sitting in three-dimensional space. Okay, so it's a curve, a closed curve in three-dimensional space. Well, three-dimensional space is full of a quantum field. So roughly speaking, you just integrate the quantum field around the knot, and then take the trace. You get an operator, so you take the trace of it. The trace is what we're going to be talking about with UHF algebras, by the way. That's the secret of classifying UHF algebras, because the trace computes the K0 group. Okay, that's not how Dixmier said it. It was almost what he said, but he referred to the Murray. He said that he pointed out that the trace computes the Murray von Neumann semigroup for UHF algebra. The trace of an idempotent gives you the two projections are Murray von Neumann equivalent if they have the same trace. Okay, and the same canonical trace. By the way, what are the UHF algebras? Where you take that's the case where all these algebras are just a single direct summand. Okay, and because if you have one finite dimensional algebra contained in another, then it's just the same as if the saying that the second one is the first one is M n1, and the second one is M n1 time tensor M and no, it's definitely going to be, the first way you see it is it's a larger matrix algebra if the inclusion preserves the unit, and it's a larger matrix algebra which is M sub M sub M. Then M is a multiple of N1, so it's N1 times N2, okay? But then you have any matrix algebra which over it's not a prime number. The order is not prime, what you call the order or the size. If it's not prime, if it's a product of two numbers, then what can you say? Because if you have Mn1 and 2, then you could ask about how is that related to well, first of all, it will contain Mn1, but how will it be? And it will contain Mn2. But how is it related to the both of them together? Anyone that hasn't studied this? Anyone who doesn't already know it wants to tell me? That's a funny question, right? Okay. All right. Well, it's isomorphic to a very canonical construction coming from Mn1 and Mn2. And by the way, how does it contain? Well, it's just okay. I'll just say it right out. It's Mn1 tensor as an algebra, Mn2 tensor product algebra. You take the tensor product vector space, and then the natural product. You extend the product in a natural way, coordinate-wise, component-wise product. You have two elementary tensors, then you multiply the first components and then multiply the second components and take the tensor product. That's that, and then you extend it by linearity. That's the tensor product algebra, and it's a larger. It's isomorphic to a lot of matrix algebra that contains. What's the inclusion? What's the inclusion? Well, if you look at Mn1 tensor the unit, instead of all little things, instead of all things a little a tensor 1, that's a subset of the tensor product, and it's a subalgebra, and it's isomorphic to it's equal to Mn1 tensor 1, okay, which is isomorphic to Mn1. Is that clear? Okay. Well, what Lim did was look at an increasing sequence, a single matrix algebra at every stage. But the way I want to look at it is look at it as an increasing sequence of finite tensor products. So the second, first matrix algebra is Mn1. The second one is the tensor product of 2 because it's larger, and the third one is even larger. So you have a Mn and a 3. Okay, and then you just keep on going. Okay, and then you take that's sort of those dots mean you take the union. Okay, that makes sense. So that's that somehow already constructs the union, increasing union. Okay, because you say you can define it. You take all finite tensor products, A1 tensor A2 tensor A3 tensor 1, and so on. So you can always repeat the 1. You can repeat infinite many 1s. That's how a tensor product is. That's how the infinite tensor product is defined. Infinite tensor product of vector spaces. If you take a fixed vector of each vector space, then you can define the infinite tensor product by saying it should tail off a finite number of components, and you tail off with the same one later. Okay, that's the infinite tensor product. Yes. Yes. Of course, if they're I'm just getting to the prime. I said that. Yeah, I'm getting to the prime numbers now. Okay, that's a very good question because we've seen here that product is very important, right? Yeah. By the way, you don't want to have too many zeros. Well, as soon as you have a 0, then all bets are off. Okay, because it's a 0 algebra, and so everything will collapse. But you don't mind having a 1. The N1, each N could be 1 because that gives you a 1 by 1 matrix, which is fine. You don't see much. You don't see them very much, but they're there. Okay. And as I said, Wim didn't include the finite dimensional matrix algebras, the individual ones, where at some stage would all be after some stage will all be M1, okay? So I want to include the ones where you take M1 always after some stage, okay? Include those, but in general not. I mean, most of them will not have the arbitrary sequences of numbers. But but the point is that this sequence of numbers is not unique because if it's only for a finite tensor product, only the product n1 and 2 that's important. If the individual numbers are not important. So the point is that you use every natural number has a prime power factorization, okay? And that's unique. And so if you have these the infinite tensor product, an arbitrary infinite tensor product an arbitrary infinite tensor product, there's a canonical way to express it, okay? Which takes into account that if you just do it in a random way, then the orders of the matrix algebra components are not unique. Okay. So what do you do? By the way, why am I talking about different ways of expressing these algebras? We've already said what the class of algebras is that we want to talk about, right? And the Grimm's theorem, we can state Grimm's theorem now without worrying anymore about analyzing the algebra, because assuming we have digested the definition of K0 as a group, then if A and B are UHF, okay, then A isomorphic to B, taking the unit to the unit, this is equivalent to saying K0A is isomorphic. Actually, K0A is isomorphic to K0B. Except that we want them, we wanted to take there's a special class of there's a canonical class. If we define in terms of modules, then you have the algebra itself, okay? And if it's defined in terms of idempotent, you take the unit. In both cases, that's a special element of K0. So we'll take, we could just call it the special element. K0A and then star, if you like, is isomorphic to, so I could call this the class of the unit, or I could call it the algebra A itself as a left ideal. All right, then that's isomorphic. In other words, there's a group isomorphism of taking the special element to the special element. Okay, so that's the theorem. That's Grimm's theorem, stated in little more modern language. Okay. Yes.
Step back for M and 1 tensor N and 2. Are those commutative products or not?
Well, don't forget that it contains the tensor product. Well, okay. Well, that's a good question. It comes up with direct sum already, right? That when we're defining the K0 group, you start off with modules in our setting, then you take direct sum, abstract direct sum. Now that is not commutative. If you take ordered pairs in one set with the first component in one set and second component in the other, it's not the same as reversing it, right? Different. It's apples and oranges. But if you talk about isomorphism, then A direct sum B is isomorphic to B direct sum A. Okay, but we're not talking about isomorphism classes, okay? We're talking about constructing algebras. It's a good question, but don't read too much into the construction the first day, okay? So this is just a construction. And you get an algebra. It contains all the individual things, so it's non-abelian, unless all the n's are 1, okay? But then so it's a non-commutative algebra. But then it turns out you can classify these algebras in a very simple way. In fact, this is true. And one reason to study the things more is that in fact, the K0 groups are subgroups of the rational numbers. They're subgroups of the group of rational numbers containing the number one. They contain the number one, okay? And in fact, they're isomorphic in a way which preserves the number one, if and only if they're equal. Okay, so that's anyway. I hope I'm not saying too much too fast. This is and if you look up Glim's paper, it won't quite look like this. Okay, Dijksmee's paper will start talking about subgroups of Q, but he doesn't talk about the K0 group. He doesn't, whereas he does talk about Murray from Emily equivalent. So, this is a very important theorem. It started. It was one of the fundamental theorems in the whole subject of operator algebras, which is a pure subject in the I mean, it's a pure mathematics subject studied for its own sake, but also for many applications. I think I mentioned the not so much an application to theoretical computer science, quantum computing, but the other way around. So they're clearly extremely close connection with a lot of fields of mathematics. All right, but there'll probably surely be someone coming in. Thank you.